Chapter 14 is carboxylic acids and esters. All right, let's put the chapter 13 away, or up here. Turn it in. Let's turn our attention to chapter 14. Very important chapter. We're going to get into carboxylic acids and esters, and that'll probably split the chapter in half. Esters are formed from carboxylic acids. So before you can really kind of understand an ester, you need to know the structure of a carboxylic acid. You're familiar with carboxylic acids. Vinegar is 95% water and 5% a carboxylic acid, acetic acid. All right? These are organic acids. They're weak acids compared to the mineral acids that we use in the laboratory often, like HCl, sulfuric acid, nitric acid. Those are very strong mineral acids that can drive the pH down to about 1 or less. These carboxylic acids will drive the pH down to about 3. Knowing that pH 7 is neutral, so you're moving down to a pH of 3, which is definitely acidic, but it's not acidic to the point where it starts tearing up tissue or anything like that. So the acid you actually have in your stomach is a very strong acid. Your stomach can get down to a pH of 1. I mean, you eat a steak, and your body needs some help digesting that steak, and it uses strong acid to digest the steak. All right, but vinegar is a weak acid. Carboxylic acids. The carboxyl group. All right, what that group looks like is like this. That's the carboxyl group, and there's where you could write an R there, which means wherever you see a carboxyl group like that, you are looking at a carboxylic acid, where the R is some other kind of organic substituent or a hydrogen. Okay, vinegar contains acetic acid. Lemons and citrus fruits contain citric acid. Apples contain malic acid. These are all going to have that carboxyl group on it, or in some cases 2 of them. All right, so you have a carbonyl, a carbon-oxygen double bond, and an OH on the same carbon. Okay? So this doesn't mean, earlier on in chapter 13 we had a aldehyde that also somewhere on another carbon had an OH group. That's not a carboxylic acid. This hydrogen is not going to be acidic or dissociable unless it's in this configuration. You've got this carbon containing 2 oxygens and a hydrogen. And so they're really drawing the electrons in here, and this hydrogen can come off or dissociate into water, and that's what drives the pH down. This is an acidic hydrogen. It can become an H+ ion. All right, R can even be an aromatic. So there's benzoic acid. We'll see here in a minute. Benzoic acid. These molecules are even more polar than alcohols. Okay, we learned that alcohols are more polar than alkanes. They have higher boiling points. These are even more polar than the comparable alcohol, and they even have higher boiling points. Polar molecules. We'll get into the naming in a moment here. Here's 3 carbons long with a carboxyl group on the end. Propane, we're going to drop the E and add oic acid to it for the IUPAC name. This is the IUPAC. Propanoic acid. We actually add the word acid to it. Propanoic acid. So we'll dive into the nomenclature a little bit more. Physical properties, like I've just been saying, somewhat polar, as a matter of fact, more polar than anything else we've seen so far. This is about as polar as it gets. Sharp, sour taste like vinegar. Okay, you can tell when you add a pickle and you all pucker up because of the pickle, because of the vinegar that's in it. It's got a kind of a sharp taste to it. All right, this is kind of showing the hydrogen bonding. If I drew a line down through here, what we're looking at on the left is just how the carboxylic acid would hydrogen bond with itself, with another molecule. Not with itself per se, but one molecule, the carboxylic acid, hydrogen bonding to another molecule. And so here's your carboxyl group here. And you can see it all can get involved in hydrogen bonding. We got a hydrogen-oxygen bond over here. We got an oxygen-hydrogen bond here, lined up oppositely because of their opposite charges. And then even the carbonyl, the carbon-oxygen double bond, is an area of negative density. And it can hydrogen bond to another OH on another carboxylic acid molecule. So this is what's giving it kind of added polarity, is that you got this and this in the molecule. Okay, in the same way they can be attracted to each other because of the polar bonds in them. They can be attracted to water molecules because water molecules have OH bonds, just like this does. Here's an OH bond. So it can be attracted here, hydrogen here, another water molecule to the carbonyl, and you get all this hydrogen bonding. So this is attraction between molecules. And so here is your alkane. Here's our comparison. We're looking at alkanes. We're looking at comparable molecular weights. Comparable molecular weights, but what I want to look at is an alkane. I want to look at the alcohol, and I want to look at the carboxylic acid. All right, 58, molecular weight 58, molecular weight 60, molecular weight 60, approximately 0 degrees centigrade. Approximately 100 degrees centigrade, and I'm just rounding these off, approximately 120 degrees centigrade. So the carboxylic acid boils 20 degrees higher, which is on a macro level an indication of stronger intermolecular forces. For that acetic acid, for example, for acetic acid, which is what we got right here, for those molecules to go into the vapor phase, they have to break that attraction to the other acetic acid molecules that are in that liquid phase. And so you need more energy to break the bonding that's occurring between molecules. And then notice right down here, it's worth keeping the aldehydes and the ketones in perspective, approximately 50 degrees centigrade. All right? So very mild or low intermolecular attraction, moderate intermolecular attraction, some polarity but not very polar. Alcohols are polar and carboxylic acids are very polar. All right, so these here have water solubility. These are soluble in water because of that polarity. So it affects solubility, it affects boiling points. These are the two physical properties that are affected. All right, in your homework, and I didn't bring your chapter 14 homework. I'll open it up, I'll bring it, what is today, Wednesday? Okay. You can either bring one up. I can bring it on Monday. I will open it up on Canvas, and I'll probably put a pile of them up in LOH 306 if somebody doesn't want to print it off themselves. Okay, I'll try to get them printed today and leave a pile of them up there. How many of you are in my lab at 2 o'clock? No, 2 o'clock lab. No. Is that what? Do I have a lab at 2 o'clock today? I think so.
Yes. Unless you want to cancel.
All right. I'll try to bring some to the lab. But we'll get them out there. They won't be due. It won't be due on Monday. Probably due next Wednesday. Your chapter 14 homework. But the very first question, I think, has a bunch of molecules and pairs of molecules. And it says, which one of these will have the higher boiling point? All right? So if you want a little hint, go back and look at this and just see how they line up. And then look at the pairs of molecules. Where is that molecule? Am I comparing an aldehyde with an alcohol? Okay, if I'm comparing an aldehyde with an alcohol of same molecular weight, which one will have the higher boiling point?
Alcohol.
The alcohol. Okay? Because this is telling you the trend. Lowest boiling point, middle, higher, highest. If you're comparing comparable molecular weight molecules. All right, let's get into nomenclature. We've touched on it already. Longest chain, always find the longest chain. Number 1, find the longest chain. 1, 2, 3, 4. It's the longest chain. Number 2, since we are talking about a carboxyl group, and that's what's going to get drawn into the parent name, it's going to dictate where we start counting the chain. The chain begins with that functionality. So that's carbon number 1, 2, 3, 4. And so we got a bromo group on carbon number 3. It is a carboxylic acid, so we're going to take butane, which would be the name of the alkane, drop the E, add oic acid to the name. And we have butanoic acid, and it's going to be 3-bromo, 3-bromo butanoic acid.
Do we have to write 1 for butanoic?
No, you don't have to write a 1. This is like an aldehyde. We know that it has to be on the end. There will be maybe one example. Well, we'll see here. You can have one on each end. You can have one on each end. And that would be a dioic. See, if there are 2 carboxyl groups are present, then it's a dioic. And I'm not sure you even need numbers there because it still has to be on the 2 ends. So one's going to be on carbon number 1, one's going to be on carbon number 4 by definition. Okay, here's some other examples. I'm not sure, but I think there will be a slide coming up shortly that shows you what you need 3x5 cards on. This is certainly one of them. All right, vinegar is made, and even if you go to HEB and you see it'll say it's 5% acetic acid, it won't say it's 5% ethanoic acid. I'm not going to say that. Even though that's the IUPAC name, it's like your nickname. You go back to high school and people don't even know what your name is. You know, they just know your nickname. All right, you picked up a nickname in the 9th or 10th grade, and you know, by the 12th grade, you ask somebody, what's her name? I don't know her name. I don't actually know what her first name is. Just know her nickname. Same way with acetic acid. That's the only name that really sticks. So, but that's not an IUPAC name. It's a common name. You don't need to know all of these. So let's just use these as to get into the naming. 2 carbons, ethanoic acid. We're looking at the IUPAC name. 3 carbons, propanoic. 3-methylbutanoic. Here's hexane dioic. Now, in other cases we had like hexadiene. Here we actually we pull the E back in because there's two consonants right here. So we actually say hexane dioic acid, and we don't have the numbers in there because those two carboxyl groups have to be on the two ends of that 6-carbon chain. And that's your adipic acid. You don't need to know these. We'll have a slide later, I think, that kind of shows you these Greek letters and how they're used. I won't dwell on it right now. There's propane dioic or malonic acid. So a bunch of these are naturally occurring carboxylic acids. Yes?
Did you say we need for the 3.5 part?
Which ones?
Yeah.
Well, so far the only one is that one. But there's another slide that I think lists all of them. This one. Very next slide. Okay, very next slide. Yeah, so all of the blue ones, all the ones in blue. Let's see, all those I've got checked. I don't typically have you learn palmitic acid. I do want you to learn oleic and stearic. Stearic is a saturated fatty acid. We will come back to stearic and oleic in chapter 17. Oleic is an unsaturated fatty acid. I think we'll look at those structures here in just a minute. But let's look at the top 4, which are short little carboxylic acids. And I'll go through some of this pretty quickly. Formic acid. So formic acid, you just have this sort of thing right here. There's your carboxylic acid and a hydrogen on it. And you can see the way they're writing the carboxyl group. COOH. One of those, the first O is a carbon-oxygen double bond. The second OH is just a hydroxyl group. So HCOOH is formic acid. Fire ants, they bite you, and you feel like you're on fire, you're itching, everything's itching. They've left behind a little bit of formic acid. And that's what's so irritating in their bite. That's what's irritating the bite. Now, I've given this suggestion, and I'll give it again right now, but I did get one person come back and say, Mr. Riak, that didn't work. But I don't know. Maybe they had bad baking powder. I don't know what it was. But if you get bitten by a bunch of fire ants, all you need to do is get some baking powder, put it in water, and then wipe it on the bites.
Really?
Yeah, because that is a weak acid. Baking powder is a weak base, and it neutralizes the formic acid.
So do you want it more like a paste?
I wouldn't think so. I would think a wet cloth with it in there, because you need the solution so that the baking soda can get to the formic acid. And what may not have worked is, I don't know, it might have been 3 hours later that she tried to do it, and there was enough of a barrier being formed already that it didn't neutralize the formic acid. But I think if you do it quickly enough, it'll neutralize it.
And that's for ant bites, you said?
For what?
Is that for ant bites, you said?
For ant bites. Someone asked me, what about mosquito bites? And I said, I don't know. I'm not an expert on bites, but know a little bit about formic acid. All right. And all this is, I have to hand out forms, and you sign it and say, this disclaimer, I'm not qualified to advise on ant bites, but take the suggestion for what it's worth. All right, so you need to know both of those names for that. That's methanoic acid. That's the IUPAC name. Its common name is formic. Okay, you saw just in the last chapter, formaldehyde was an aldehyde with one carbon. Formic acid is a carboxylic acid with one carbon. Likewise on the second one, we already mentioned that one, acetic, ethanoic. And the acet prefix, even in the common name, typically is pointing to two carbons. So that's acetic acid. That's the Latin acetum for vinegar. Propanoic, that's the IUPAC, or propionic is the common. Swiss cheese. Butanoic is also called butyric, and that's a pretty common name for it. You say this is butyric acid, and that is the acid when butter goes rancid. It forms that acid in there. It's forming butyric acid. All right. We'll look at oleic and stearic here, I believe, right now. Stearic is coming from beef fat. They really should have called this stearic.
Yeah.
Thank you. If it had been discovered in Texas, it would have been stearic acid. But somehow it got STEAR. Let's see if we have those. I think these show up in the next couple slides. So there's citric acid. Look at that. It has a whole bunch of carboxyl groups on it. Lactic acid from yogurt or from strenuous exercise. And you get your muscles get sore from lactic acid. Adipic acid from beet juice. So there's a lot of naturally occurring carboxylic acids in fruits and vegetables. All right, notice, well, this and this are the same. This is not, all right? So let's name some of these here. Yeah, go ahead and name. Put some names on 2 or 3 of those, and then we'll share them together in a minute. Name as many of those as you can. What's the longest chain on the first one? 5. So pentanoic. And what else? Bentanoic acid. And then what else is on there? 2-bromo out in front. 4-methyl. All right. I'm going to skip over the next one. What's the longest chain on the next one? So 8, so it's octanoic acid, and then you just got to put all those bromos. Oh, now we're going to put all the bromos together, aren't we? What are the numbers?
2, 3, 4, 5, 6, 7, yeah. 2, 5, 7.
2, 5, 7?
5, 7.
Everybody agree?
Tri-bromo.
Tri-bromo. Here's 1, 2, 3, 4, 5. Okay. Okay. 2, 5, 7 tribromo octanoic acid. Okay, now this one down here, ignore that for a minute. What would you call that? Cyclohexane. So just take off the E. Cyclohexanoic acid. Okay, just drop the E. So cyclohexane, look at what it would be if it were an alkane or didn't have that carboxyl group on it, and then change it. Cyclohexanoic, didn't write that word. Hexanoic acid. Okay, now let's do the same thing here. Without the carboxyl group on these next two, we'll look over here. What would you call that? Benzene. So that's benzene. So what do we got to do? We got to drop an E. Drop the E. Wait a minute. Benzanoic. we are going to mess with this one. Benzanoic acid. We are going to mess with it a little bit. Instead of benzenoic acid, it's going to be benzanoic. Benzanoic acid. So we are changing a little bit. But they're both benzenoic acid, just two different ways of drawing them. Yeah.
Do you know close in the spelling? Like, let's say if we put like B-N-Z-E, anoic, would you count it wrong or would you?
Probably. All right. On the exam, and you may see some places where spelling was counted off, like if it should have been an E and it was an A for an alkene or an alkane, that's critical misspelling. If someone slaughtered the word toluene, and had an extra letter in there or something like that, I might not have taken off. But if it actually does change the functional group it's in, then I count it wrong, or count some off. So, yeah, so do pay attention, particularly to suffixes. Okay, let's take a look at these two. They're comparing two fatty acids, a saturated fatty acid and an unsaturated fatty acid. Yes?
So, for the middle one?
Middle what?
On the last slide.
That's the same thing.
That's the same thing as...
These are the same.
This is a different way to draw it.
Okay.
Yeah, instead of having these alternating double bonds, we draw a circle. You can do it both ways. You can put the alternating double bonds in there, or you can just draw a circle inside there. And so that's an aromatic carboxylic acid. Same question, Gabriel?
Oh, no, I was just...
Okay, so this here, there are 16 of these CH2s in there. So you got, it's an 18 carbon, 18 carbons long. Both of these are 18 carbons long. So let me try to draw this here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh man, I'm not going to be able to do it. 13, 14, 15, 16, 17. Okay, it is not soluble in water. Yeah, this end is polar, but what you're learning is that when you just have too much of a non-polar tail on it, these are all hydrogens. You need to learn to draw these two fatty acids, one way, shape, or form. Here is the condensed, this condensed it down. You see you got 16 of these in here. 16 of these CH2 groups. So that's why they have it written like this. They've got a CH3 on the end, that's this thing right here. And then they've got 16 of these things. And then you could either write it as this, or you could write it as that on the end, either one. This is just a really nice condensed way of writing it. But I want you to see, we're talking about a really long carboxylic acid, a fatty acid. When we get to chapter 17, we'll be studying the things that are not soluble in water. That's not soluble in water. It's a fat. Fats aren't soluble in water. Fats and oils. This one, fat, meaning it's solid at room temperature. Olive oil is not a solid at room temperature. And then over here, oleic. Now they've just taken the hydrogen off and have changed the name to oleate, the oleate ion, if it was that way. You've got a double bond here. You see that? Not only do you have a double bond, you have it smack dab in the middle of the molecule, and it is cis. It is a cis double bond. And that's what nature makes in terms of unsaturated molecules. It makes cis bonds. Not just randomly, some cis, some trans. They're cis. So if we wanted to draw that one, we could have a CH3, and then we would have 7 of these, and then we would have a double bond, and then we would have 7 more of these, and then we would have our carboxyl group. That's oleic acid.
We probably need a card for these, right?
Yeah, you may need a bigger card. Write small. But yeah, those are on the list. Those are on the list as 2 that you should know. You can see they have a common name. I mean, it could be let's see, it does have another name. Decaoctanoic acid or something. Is it? Yeah?
That's going to drive me to drinking. Like alcohol. I'm gonna be walking around with an OH because that's a lot.
Okay, I absolve any responsibility for your decision in that. That's a personal matter.
That form on the bottom where it says
One other option is to just say, I'm going to take a miss on these 2 molecules and learn everything else. Yes?
the form on the bottom, that's how you want us to write the condensed form for that one?
That would be one way of writing it, yeah.
Okay.
I would not want you to put these 14 together, because then it kind of,
Really long.
well, no, it kind of pushes the double bond somewhere else on there. See, you got 7. 1, 2, 3, 4, 5, 6, 7 over here, and you got 1, 2, 3, 4, 5, 6, 7 of them over there. That's why I'm writing it that way. And you'll see later in chapter 17 why that double bond is just not anywhere. It's really smack dab in the middle of the molecule. Nature actually does know what it's doing. We look into it to figure out, why is it doing it that way? Why does it do it that way? Why does it do a double bond right there? And why is it always cis? Okay?
Are they both saturated fatty acids?
No. Asenath asks a good question. This is a saturated fatty acid. This is an unsaturated. Remember, when you see a double bond, that is an area of unsaturation. This is not a polyunsaturated fatty acid. Poly means many. This is only one. This is a monounsaturated fatty acid, oleic acid. Okay. This is the fatty acid that's in olive oil. This is in olive oil. And this is mostly in beef fat. We'll see, we'll go into more detail on that in chapter 17. Reactions. Okay, this is all review. If I were to ask you to sit down and think about it, how could you make a carboxylic acid? You say, well, I know 2 ways of doing it. I could take a primary alcohol and oxidize it all the way over here with a strong oxidizing agent. I make a carboxylic acid. Or I could start out with an aldehyde and oxidize it, and it will become a carboxylic acid. All right? You already have that in your toolkit. So this is just kind of review. How do you make a carboxylic acid? From a primary alcohol or from an aldehyde? And you're oxidizing these. There's two ways to make a carboxylic acid. All right, so we're all the way down to the end of this slide that I keep showing you. We're at the end of oxidation here. The only thing we could do with this molecule, with acetic acid, for example, to oxidize it any further would be burn it. Now we could burn it, but we could never convert it back into an organic molecule from there. We just convert it into carbon dioxide, it's gone, disappeared. So is there another step? Yeah, but that's just the very unsophisticated chemical reaction, which is burn it. All right? This stuff is all sophisticated. We're converting an alkane into an alcohol, into an aldehyde, into a carboxylic acid. That whole direction is oxidation. Or we could start with a carboxylic acid and start reducing it down to an aldehyde, to an alcohol, or back into an alkane. That's reduction. Yeah, this is showing you all the way here where bam, it's gone, can't do anything more with it, not much use to us, just goes off into the atmosphere and causes hurricanes like it's hitting Tallahassee today. Did you hear the news?
Yeah.
They basically told the people, if you haven't left, you can't leave now.
Yep, I left just in time before it starts.
Were you in Florida?
Mm-hmm. Yeah, and a couple of my other friends were there the day after, and they were like, I hope we can leave in time. Or they didn't have earlier flights either.
Yeah, because they shut down the bridges, I guess out on those breakwaters or whatever is out there.
Yeah.
They basically said the traffic can't go across these bridges anymore. Bridges are shut. So wherever you are is where you need to be. Yeah, so I don't know. It seems like every week we're hearing this. I'm driving in this morning hearing this, and I'm saying, I've heard this story weekly here for the last couple months. Okay, another fairly straightforward reaction. Remember, we're talking about well, this isn't really a reaction. This is just the dissociation of the carboxylic acid in water. But let's just take a look at it here. If I had acetic acid, and this is an equilibrium, I would get this ion plus the hydrogen ion. This is acetic acid, and it's going to form now. Here's what we do now. We drop the IC and we add ATE. It's going to form the acetate ion, anion, negatively charged ion, and the hydrogen ion. Don't get the hydrogen ion mixed up with hydrogen. When I just talk about hydrogen, I'm talking about H2, elemental hydrogen. This is an acidic proton floating around in the water. All right, and so this is in water. It is in an equilibrium. So it can reform this. It can redissociate to that. And as a matter of fact, and this is review from 1305. You should remember this from 1305. About 99% of it remains molecular like that, and about 1% dissociates. So that's not a, don't get mixed up with my 1%.
So that's an ion with a negative charge?
Yeah, that is a negative charge right there. That's a negative. That's not a bond. That's a little negative. The acetate ion, you can see in general we're talking about a carboxylate ion. The carboxylic acid forms a carboxylate ion. Let me just see here where we are, how we are progressing. Yeah, that's probably good enough. Okay. We will get into the acid-base reaction. That was not the acid-base reaction. That was just simple dissociation. We'll get into the acid-base reaction and really plow into esters on Monday.